Okay, everyone, if we could please sit down. Good afternoon. It is really my pleasure to introduce this week's colloquium speaker, Carlos Badenes. Carlos received his PhD in astrophysics from the Barcelona Politecnica. His advisor was Eduardo Bravo. Carlos subsequently moved around quite a bit and had postdoc positions at Rutgers, Princeton, and a joint position at Tel Aviv University and the Weizmann Institute of Science. He then moved to the University of Pittsburgh, which is where he is now as assistant professor in the Department of Physics and Astronomy. Carlos's research is generally focused on Type 1a supernova explosions, their binary progenitor systems, and the supernova remnants that they leave behind. And as we learned earlier this afternoon at the ITC Luncheon, he also has interests in planetary nebulae. So we are very fortunate to have Carlos with us today, as he will undoubtedly leave us with a memorable talk on how the remnants of Type 1a supernovae inform us about their progenitor systems. Carlos, please.
Thanks, Danny. Thanks to everyone. It's always really great to visit this place. And I have to apologize in advance because I've had a cold for the last week and my voice is doing funny things. So if I croak, I'm gripped with emotion at the beauty of the data. You can interpret it that way. The Persistence of Memory is, of course, a title of a very well-known painting. It's this painting by my fellow Catalan Salvador Dalí. It's been, this is surrealism, so you can think whatever you want. But it's been construed as an allegory for the passage of time, and I keep using it as a device in talks because I find it's a very powerful image. Because pretty much this is what supernova remnants, the role that supernova remnants play in this game too, is a repository for memory. So if you thought the talk was about mustache grooming techniques or surrealism, I'm going to have to disappoint you. It's about supernova remnants, and the motivation is up there. The progenitors of Type 1a supernovae remain unidentified. And whenever you have a hard problem, it's always good to look at it from many different points of view. Supernova remnants provide a different perspective on supernovae, and today I'm going to focus on two particular aspects. One is the interaction with circumstellar material that supernova remnants tell us things about. Another is the stable iron peak elements that we can see in their X-ray spectra, which also tell us important information about the progenitors of Type 1a supernovae. So, just to set the stage a little bit, and this is a very broad topic, and it's a very active area of research, so it's impossible to cover everything. But of course, everyone here knows that supernovae are rare optical transients that last for weeks or months, and they have peak magnitudes that rival their host galaxies. Right? They're about yay bright. Supernovae are classified, of course, by their optical spectra around maximum light, and we've come up with this classification, which is essentially something we live with, not ideal, but informative enough. The Type 1s have no hydrogen, and the Type 2s have strong hydrogen. Within the Type 1s, 1As have silicon, 1Bs have helium, and 1C have neither silicon nor helium. Now, after decades of work, we've come to realize and bring some physical understanding into this that the Type 2s, 1Bs and 1Cs, are core collapse supernovae. They're the result of the gravitational collapse of the core of a massive star. And we know this because not many, but a handful of progenitors of this supernovae have been identified in things like pre-explosion images and such. However, the thermonuclear supernovae, the Type 1a, the situation is not so clear. Now, through the years, we've put together a sort of a shopping list of things that Type 1a supernova progenitors should have. And this goes a long way towards explaining why this is still an unsolved problem, because it's a pretty daunting shopping list. We know the progenitors must be small. We know this because we can model the early light curves of things like supernova 2011 Fe. And you can constrain that any kind of flash from a shock breakout of an object that was there would have to be below these detections of the initial expanding fireball. And that essentially gives you an upper limit on the radius of the thing that exploded. It's a very nice work by Peter Nugent and Josh Bloom. And the number that you get is a few percent of the radius of the sun. And the only things in stellar astrophysics that are that small are white dwarfs and neutron stars don't explode, so there must be a white dwarf in the progenitor. It's really nice result. They must also be faint. If you look at deep pre-explosion images of nearby supernovae that have been collected by HST, you get very interesting upper limits. This again is for supernova 2011 FE. And these are limits that rule out many accreting white dwarf systems like RS-OFF in our own galaxy. And also most red giants and essentially also main sequence stars that are more massive than about 4 solar masses. So these are very restrictive upper limits. And finally, of course, type 1a means that there's no hydrogen, and we know these objects are hydrogen poor. But they're not just hydrogen, they're extremely hydrogen poor. You can look at nebular spectra of nearby supernovae, and again, you look at where the H alpha line should be, and there's really nothing there. And the upper limits on the mass of hydrogen that's around the progenitor at the time of the explosion are very small, so a few percent of a solar mass or even lower. So how can you make sure you satisfy all these requirements? Well, there's this sort of unified scenario that's been around for a while, it says that basically type 1a supernova are thermonuclear explosions of carbon oxygen white dwarfs that are somehow destabilized by mass accretion in a binary system. Now, we know there has to be a white dwarf in the progenitor, and white dwarfs have the irritating habit of being stable, so you have to do something to it, hence the binary companion. And the wonderful thing about this picture is that it really does explain a number of things very well, right? Explains why there's no hydrogen in the spectra, because you wouldn't expect it in such a system, at least in principle, the energy budget, the light curve decay rate. But there are key details that still remain obscure. And this is what we refer to as the type 1a supernova progenitor problem. In particular, what is the nature of the companion and exactly how does this white dwarf get to the extreme situation that leads to explosion, right? Of course, this is it's obligatory to mention on a talk on type 1a supernovae that the fact that you always explode the same kind of star in more or less the same kind of way leads to the striking uniformity of these events. If you take the light curves of type 1a supernovae and correct for the fact that the bright type 1a supernovae have wide light curves and the faint type 1a supernovae have narrow light curves, you end up with something that's pretty close to a standard candle, and that's what allows you to do cosmology. And a lot of the interest in type 1a supernovae comes from this. But there's an underlying stellar astrophysics problem that still hasn't been addressed. And through decades of working and on this and not necessarily making an awful lot of progress, people have begun to sort of take apart these ideas and put them together again. So these are standard scenarios that people modify and re-examine continuously. And I don't pretend to cover every possible detail here, but essentially you have two possibilities. Either the white dwarf companion is a normal star or slightly evolved star that is not degenerate, and then you talk about the single degenerate scenario. And this is the old textbook picture of type 1a supernovae that many of us have ingrained in our heads. There's a Roche-Loeb overflow through the inner Lagrangian point. You form an accretion disk because you need to get rid of angular momentum, and this accretion disk feeds on the white dwarf that then slowly grows in mass until it gets close enough to the Chandrasekhar limit that it becomes unstable. Right? So you expect this kind of explosion to happen when the white dwarf is close to the Chandrasekhar mass, and you expect some amount of circumstellar material around the progenitor because it is very hard to envision a situation where this kind of feeding process would be 100% efficient. The other possibility is that the white dwarf companion is another white dwarf. Then you talk about double degenerate systems. And in this case, the theoretical picture is much simpler. You have a binary system with a short period. It emits gravitational waves. The orbit decays, and this leads to the merging or collision of the two components and an explosion that doesn't necessarily have to be close to the Chern-Secker limit, right? In this case, in principle, you don't expect a lot of circumstellar material because white dwarfs are evolved objects. And again, this is a simplification of a very complex field, and there are many individual variations on these scenarios, but this is roughly the playing ground. Now, of course, since no progenitors have been identified in pre-explosion images, people try to constrain these two scenarios with indirect means. So you can, for instance, look for surviving companions inside young supernova remnants. If this is what's going on, this star should survive the explosion. Yes, it's next to an exploding supernova. Yes, that is going to do something to it, but stars are dense and hard to disrupt in general, so some sort of companion should survive. And this has been done by a number of people using a number of different techniques. And whenever these searches have been done, they have either led to upper limits or ambiguous results. A very good example is this Hubble Space Telescope image of supernova remnant EO 509. And you don't need to do detailed analysis to see that there are no stars at the center, which is where you would expect to find the surviving companion. Naively, you think this would at least be easier to interpret in the light of the double degenerate scenario. Another thing people have looked at, including myself, is the delay time distribution of type 1a supernovae. I talked about delay time distributions earlier at the ITC lunch, but essentially the delay time distribution is the supernova rate as a function of time. And people have looked at this using many different methods. In particular, Dan Maus has done a lot of work on this. He always likes to show this plot and say, this is a decade of my life on a plot. You can see that Danny is a big player here. And to cut to the chase, this delay time distribution has power at pretty old ages, beyond a few gigayears. And as far as the data can tell, it looks pretty much like 1/t. And these are both predictions from the double degenerate scenario in binary population synthesis calculations. Whenever people calculate delay time distributions for single degenerate scenario progenitors, these tend to taper off after a few gigayears because essentially you ran out of stars that are massive enough to drive the white dwarf to the Chern-Secker limit. So again, naively, you would think this supports the double degenerate scenario. Another piece of work that is important, I think, is that we've been able to measure the merger rate of white dwarfs in the Milky Way disk. And this is work I did with Dan Maus also, and we did this with the Sloan Digital Sky Survey observations of white dwarfs. All of them have more than one visit, so you can do statistical analysis on the distribution of radial velocity shifts. And I don't want to bore you with the details, but essentially you get a merger rate that is of the order of the type 1a supernova rate in an SBC type spiral. Okay? I have to insist that this includes all white dwarf mergers, but it is an interesting coincidence, if it really is a coincidence. So all this looks pretty promising for a double degenerate scenario, but there is always a fly in the ointment, right? And in this case, it's more like a hippopotamus in the ointment. There are, again, I'm summarizing a very active research field, so I can possibly mention everything, but there are two things that I definitely want to talk about. One is this appearance of blue-shifted variable absorption lines in the spectra of some type 1a supernovae. Okay? And this is a very interesting observation and now has been interpreted by different groups to either support the single degenerate scenario or the double degenerate scenario, or both or neither. So I'm just going to leave it there. I don't want to dismiss this observation. I think it's very interesting. Personally, I think that naively this would be easier to envision in the single degenerate scenario because it's some kind of circumstellar material. But we don't know exactly how much or exactly where it is, right? And that makes it very hard to have a physical interpretation for it. Another recent piece of work that I think is very important is this statistical analysis of type 1a supernova light curves by Richard Scalzo and collaborators. And what they did is here they got an estimate for the distribution of ejected masses. And they found that there are is a spike at the Chandrasekhar mass, but a significant tail towards lower masses. Now, again, I don't want to sound like I'm dismissing this work. I think this is very important, and I think it's a beautiful paper. But it's really hard to play this game. Number one, it's a statistical measurement. You don't really know anything else about these supernovae because they exploded very far away. Number two, it's very hard to get an absolute scale on this ejected mass. You're essentially making assumptions about the radiative transfer in the light curve, that the diffusion time of the photons, that's what controls the light curve width. And it is hard to pin an exact mass scale on this. Naively, again, this would point towards at least a mixture of scenarios, but it's hard to see. Again, people keep looking for what's called a smoking gun, a single and ambiguous a measurement that can either falsify or not a given scenario, and that is very, very hard. So I'm going to present now some results on circumstellar interaction in type 1a supernova remnants that bring kind of new light into this problem. This is the Kepler supernova remnant, kind of the poster child for circumstellar interaction in type 1a supernovae, but we'll get into the details later on. So the way circumstellar interaction, or the way people look for circumstellar interaction in type 1a supernovae, is different temporal scales. And again, this is something when I'm talking about circumstellar interaction here, I'm talking about dynamical circumstellar interaction, something that can slow down the supernova ejecta. Okay, so this wisps of whatever it is, that doesn't qualify as dynamical circumstellar interaction. There's something there, but there's probably very little mass in it. But if you think of the single generate scenario, there should really be some mass around, because that can possibly be 100% efficient, the mass growth of the white dwarf. So essentially, you're trying to constrain the mass loss rate of the progenitor and hoping that you can get to some interesting measurements here. You can do this either at early times by looking at the rise of the light curve, and this would be on physical scales of maybe 10, maybe 100 AU, and whenever people have done this, again, they haven't detected anything. So there seems to be either no accretion disk or no extended envelope, or at least none that you can detect. You can do it at intermediate times, in scales of weeks or months, and this is typically done in the radio and in the X-ray. And again, whenever this has been tried, only upper limits. And now with this nearby supernovae, 2011 Fe and 2014 J, these upper limits are getting pretty restrictive. This is nice work by Laura Chomyuk. And as you can see, there's no detection. And this is constraining the mass loss of the progenitor to about 10 to the minus 9 solar masses per year, normalized by velocity. And then again, you can look at late times at supernova remnants. And I contend that this is a very interesting way to approach the problem. And it's very important to do it this way. Why? Well, because you're probing different physical scales. And this is very, very important. Now, if you think of density and radius, right, and naively assume r to the minus 2 profiles for different mass loss rates and different velocities, this would be typical of a escape velocity of a red giant. This would be typical escape velocity from a white dwarf. So, be agnostic about what can be going on. In radio or X-ray supernovae, a few weeks after the explosion, you probe this regime. For supernova remnants, you probe this regime. So you're going from something that's the size of the outer solar system to something that's parsecs. And this is really important, because if you think about when this material was ejected from the progenitor, in the case of radio or X-ray observations, you're probing, tens or hundreds or maybe thousands of years. In the case of supernova remnants, you're probing tens of thousands to maybe millions of years. And this is comparable to the Kelvin-Helmholtz timescale of an evolved star. So these are timescales that are relevant for the evolution of the progenitors, and that's why you want to look at it. The way we constrain the structure of the circumstellar material in a supernova remnant is by looking at the spectrum. Supernova remnants are young. Their ages are small compared to the equilibration timescales in the shock plasma. And what you get is this typical non-equilibrium ionization situation where the X-ray spectrum is controlled by a parameter we call the ionization timescale, the NET. Right? High ionization timescale results in high centroid energies and line fluxes for the relevant lines in the X-ray spectrum. And this means that there has been, this is of course a collisional process that scales like density squared. It means that the material is interacting with something. The denser the circumstellar material or the ambient medium, the higher the ionization timescale for the same age of the supernova remnant. You can see this here for the silicon line. As you increase the ionization timescale, the centroid goes up and you even get the hydrogen-like line here. The details don't matter that much, but one thing that's, I think, a very good idea, and I can say this clearly because it was not mine, it was an idea that Hiroya Yamaguchi had, is instead of using silicon, you use the iron K alpha line. Now, iron K at 6.5 keV is not where you would start to look because it's a relatively faint line. But because iron has 26 electrons, it gives you a huge dynamical range in ambient medium densities that you can probe using this line, right? If you look at the centroids of this line in different supernova remnants, you can get an idea for how much material have they interacted with. One challenge of doing this, playing this game at 6.5 keV is that you need a lot of effective area here because again, this area is, this line is faint. So the best satellite to do this is not actually Chandra or XMM, is a Japanese satellite called Suzaku, which has the best combination of effective area and resolution and low background at this particular energy. So you can collect data for different supernova remnants in our galaxy and in the Large Magellanic Cloud, and you can look at the iron K alpha luminosity as a function of centroid energy. And after the painstaking job of reducing the data and running the models and putting everything on a plot, you end up with something that's a scatter plot. Very uninformative and, of course, very disappointing, right? But it's not all so bad because you can account for the fact that these remnants are not all, they don't have all the same dynamical age. So if you just single out the ones that have a low age versus radius, so quotient between the age and the radius, and these are of course estimates, but the ones with the fill symbols, then this singles out young objects, a few hundred years at most. And if you do that, this is not a scatter plot anymore. You see clearly two sequences, one here and one there, right? And the centered energy iron K alpha separates this very clearly. You can start asking yourself, well, what does this mean? And here you're bringing the actual names of the object. I haven't told you what remnants we're talking about, right? But here are the names of the objects, and you immediately realize you're onto something. Because everything that you know for sure is a core collapse supernova, because either we saw the supernova itself, like 87A, or there's a compact object like Cas A, or we have very good analysis of the X-ray spectrum or whatever. Anything that has been a G292 is a pulsar wind nebula. Anything that we know for sure is a core collapse supernova is on this side. And everything we know for sure is the Type 1A is on this side. And this includes Tycho and 0509, which have light echoes from the supernovae, so we know where Type 1As. Things like SN1006, for which we don't have a light echo, but we're pretty sure it was a Type 1A from the X-ray spectrum. So this separates things very well. So what are these points that were in the middle that we're turning this into a scatter plot? These points are just older cousins of these two populations. So these are older Type 1A supernova remnants, and these are older core collapse supernova remnants because the ionization timescale is increasing with age, right? So you come to the conclusion that this really is a powerful diagnostic. And you end up with the Type 1A supernova remnants being over here and the core collapse supernova remnants being over there. And what's separating them is the fact that they're interacting with different kinds of medium. Now, this is of course good, and it's kind of a new method to classify supernova remnants, but what I want to bring to your attention is that this allows you to quantify the circumstellar interaction of both 1As and core collapses. And that goes directly to the mass loss rates from the progenitors. And this is an interesting problem. It's interesting even for the core collapses, because mass loss rates are the single largest uncertainty in massive stellar evolution right now, other than binary interactions, which also probably impact the circumstellar medium. So this is something to take into account. Now, whenever you see an interesting thing in the data, you want to try to interpret it quantitatively, you need models, of course. And these are models for type 1a supernova remnants, where we've done something very simple. They're actually models I calculated for my PhD thesis, and I never thought they would reach a shelf life of more than 10 years. But you can plot the iron K alpha line luminosity and centroid here for these models that are basically just Chandrasekhar mass type 1a supernova ejecta interacting with a uniform ambient medium. And you already see very interesting things. Like you take a bright type 1a model, something that has a lot of iron, it lives in a different part of the diagram than a faint type 1a supernova model. Right? So this is a crude but effective diagnostic of supernova brightness. We also consider pulsating delayed nation models. I actually don't have a lot of time to discuss this, but I want to go back to this plot, and this is the plot now where we have the data and the models on the same plot. And as you can see, just this very simple ansatz of a uniform ambient medium and Chandrasekhar mass ejecta pretty much explain everything you see. Turns out this plot is misleading, and I'll tell you why in a slide. It doesn't explain everything. But it's a very impressive agreement. Okay? The 1As are exactly where you would expect them to be, knowing what you know about their explosions and the ambient medium, assuming that they are interacting with a uniform ambient medium. Now, is this really the physical explanation? Well, I really think it is. I really think it is because you can look at other things. You can look, for instance, at radius versus age. And again, these ages are estimates, and I've omitted the error bars for clarity. This is just an illustration. But if you look at the 1As and the core collapses, remember 1As are red, the core collapses are blue, you know from basic physics that the remnants should start behaving like this. They should be more or less in a free expansion. And then at some point when they sweep up an amount of mass equivalent to their ejecta, they should transition to this other behavior, which is just the set of Taylor solution. Right? And if you look at remnants with similar radii, you find that the 1As are usually younger. And this means that they have a transition to set-of that's at a later stage, even though they have a lower mass. And again, this points in the same direction. They're interacting with a lot less material. Right? Another thing that's very important to look at, and this is very revealing actually, of course, this diagram here, this is just luminosity and centroid energy. There has no information about the physical size of the remnants, right? But you do have to look at this. And here is centroid energy, here's the actual physical size of the remnants. And again, this is a comparison between the data points and these Chandrasekhar mass ejecta models that are evolving into uniform ambient medium. And again, you find this remarkable agreement. Basically, all the remnants that we know and we can identify as type 1a behave as if they were interacting with a uniform ambient medium. That doesn't mean they are all interacting with a uniform ambient medium. There could be some circumstellar interaction, but if there's circumstellar interaction, there can be a lot of it. Okay? Certain objects like Kepler and N103b have been argued by several people, including myself and Dan Patenaude, who's sitting here somewhere, that there could be circumstellar interaction there. But again, I want you to consider the dynamics of Kepler compared to the dynamics of Tycho. They're really not that different. Whatever is going on in Kepler is not a radical departure from uniform ambient medium. Can't be. Of course, I have to remind you that this is just the one half of our sample. The core collapse remnants are all here, right? They have comparable radii. They just their iron K alpha centroid energies are much, much larger. Before moving on to the next slide, I want to draw your attention to this object over here. Now, of course, the models stop at 5,000 years, and a couple of these remnants are probably older, so G344 may or may not conform to this picture, but RCW86 almost certainly does not. We've known this for a while. We know RCW86 is a cavity explosion. It's expanding into very low, very large, very low density, very large cavity that was excavated by the progenitor. And it really is an outlier. It's dynamically unlike any other type 1a supernova remnant. And this is probably important. It could be that this one is also a cavity explosion, but certainly RCW86 is different from all the other Type 1a supernova remnants. So, as far as I know, the only way to explain that object is a fast, continuous outflow from the supernova progenitor. So, let's go back to this picture and reevaluate things. It seems that Type 1a supernovae are not interacting with a whole lot of stuff. In fact, they're all, except for RCW86, consistent with an interaction with just the warm phase of the interstellar medium. Again, this doesn't mean they're not interacting with something else, but any deviations from that should be small. You're going to say, well, I've heard this before. Not a lot of circumstellar interaction in Type 1a supernovae. This rings familiar. Well, you haven't heard it before. Not with this data and not in this regime. Again, look at the sizes of radio X-ray observations or upper limits for Type 1a supernovae and typical supernova remnants. We're making a statement that applies to physical scales of parsecs or more. And this is very revealing. This is telling us a lot about what the progenitors were doing 100,000, a million years before they exploded. And they weren't apparently up to much. Again, I don't claim to have ruled out a number of scenarios. We're actively working on this. It's possible that mild circumstellar interaction is allowed. It is possible that small cavities around the progenitors are also allowed. But again, this is remarkable agreement over 5 orders of magnitude in radius. So, you know, there's this English monk called William of Ockham who had very good advice for people who shave. So, you know, I just want to lay that out there. Okay, so steps forward from here. Of course, we're working on expanding the model grid. I have a graduate student now that's trying subchandra explosions and different kinds of circumstellar medium interaction. But again, I have to warn you, any radical deviations from this scenario are probably going to be ruled out by the data. Well, let's wait and see exactly what we can get away with. It's always good to expand the physics that's in the models. There's work here in the supernova remnant group at the CFA to do this with cosmic ray modified dynamics. And finally, it's kind of frustrating to look at this plot and have nothing to show for the core collapse supernovae, right? So smart people never want to be frustrated for too long. And this week on AstroPH, there's a very nice paper by Dan Patenaude where he has calculated models for the core collapse supernova remnants. And again, you get this remarkable agreement. The core collapse supernova remnants are more or less where you would expect them to be. Given the fact that they have the progenitors that they have, they're going to lose the mass at the rate that they massed according to stellar evolution. Again, there are objects you can't explain, and there are details here that I can't really discuss. But if you're curious about this, I encourage you to ask Dan. And of course, we're going to get much better data soon when AstroH gets launched. So this is, I think, very promising road for progress in the future. Okay, and I'm going to get onto the final part of the talk. These constraints in circumstellar interaction are very, very interesting. We need to do more modeling in order to definitely falsify or not specific scenarios. But there is one measurement that you can do with supernova remnants that's extraordinarily clean and robust and goes right to the heart of the progenitor scenario question. And this has to do with the iron peak elements in Type 1a supernova remnants. And I'll give you first a little bit of background. You've seen these models that I showed are labeled DDTA and DDTG and things like that. DDT stands for delayed detonation. And these are the standard explosion models for Type 1a supernovae. This is a paradigm that has been going around, for a long time, essentially since 1991. It's not physically motivated. It came from the mind of Alexei Khokhlov, but it does explain a lot of things very well. Essentially, you take a chance-secular mass white dwarf from your local white dwarf supplier, and don't believe them if they say that we don't have any of those. You take a chance-secular mass white dwarf, you initiate thermonuclear runaway in the central regions, and you initiate this thermonuclear runaway at a subsonic speed, a deflagration front. At some point, this deflagration front transitions to a supersonic speed, and you have a deflagration to detonation transition. That's what the model stands for. And the reason people like this model so much is because with this simple parameter, the transition at which you impose this, the density at which you impose this transition from deflagration to detonation, you can reproduce both the bright type 1a supernovae and the dim type 1a supernovae and everything in between. Now, the way you do this, and I have to apologize here because I compare my models to supernova remnants, so I take everything that's unstable and decay it. So the people who work on supernovae are going to say, well, where's the nickel 56? Well, the nickel 56 is here, and I show it as iron because, by the time you have a supernova remnant, it's all gone. So that would be a typical bright type 1a supernova model with lots of iron and not so much silicon and sulfur and other stuff. And this would be a typical faint type 1a supernova model with a lot less iron, a lot more silicon and sulfur. And the difference between these two comes from the interaction of this transition density and the fact that the burning regime in which you process these elements has to do with the peak temperature that's reached by the burning front. So going from the outside in, you have explosive oxygen burning, explosive silicon burning, nuclear statistic equilibrium, and then this regime, which is what I wanted to focus on for a minute. This is called neutron-rich nuclear statistic equilibrium, and it's a misnomer. It's nuclear statistic equilibrium, and it just happens in a region of the white dwarf. And remember, this is a Chandrasekhar mass white dwarf. Happens in a region of the white dwarf where the density is high enough that electron captures can happen efficiently during the time of the explosion. And this has a very significant imprint. This leaves a very significant imprint in the nucleosynthetic yields because it moves the equilibrium point from nickel 56 to more neutronized species like nickel 58, nickel 60, and things that eventually will decay into manganese and chromium. So you can see that the nucleosynthesis is very different here from there. Now, a very interesting development in this field has been the realization that if you take sub-Chandrasekhar mass white dwarfs, which you can get from your local white dwarf supplier, they also make viable type 1a supernova explosions. If you manage to find a way to ignite them in the center, there's very nice work by Stuart Sim and Martin van Kerkwijk and other people, you get something that's very similar. You get the iron inside, intermediate mass elements outside, and some of the other stuff at the very end. And the difference is not that much, right? It's 0.9 to 1 solar mass to 1.4, so it's a difference of about 40%. From the point of view of supernova spectra, this may not be very different from that. But this white dwarf is not dense enough to have a core where electron captures can happen. So there's never any neutron-rich nuclear statistic equilibrium material in sub-Chandrasekhar white dwarf explosions. Never. You never see this speaking nickel and the manganese here. So the yields of this neutronized species are actually an excellent diagnostic of the mass of the white dwarf at the time it exploded. Not all is so easy, however, because there is another way to make neutronized species. And this has to do with the progenitor metallicity. And again, I do not have time to tell you all the details. I'll be very happy to answer questions about it later. But essentially, more metal-rich progenitors will make more neutron-rich species because, well, this comes from the nitrogen-14 p-gamma reaction being the bottleneck in the CNO cycle. So when you create white dwarf, you end up with an amount of neon-22 in the white dwarf that scales with progenitor metallicity. And that neon-22 has neutrons, and those neutrons you can use to make stable nickel and manganese in those neutronized species. So you're looking at something that is a combination of both things. Whatever you produce in the core of the white dwarf plus what you get from the progenitor metallicity. Now, you can think of measuring this neutronized species. Of course, you have to normalize to something. So iron is a typical good choice if you're looking at supernova remnants. So if you plot manganese to iron versus nickel to iron, and you get the yields for typical Chandrasekhar mass delayed detonation models, this is where they live, right? And this metallicity arrow just points towards higher metallicity will give you more neutronized species in general. Right? But these are all models that have a core with active and efficient electron captures. Now, what happens to the sub-Chandrasekhar explosions if you plot them in the same plot? Well, this is what you get, right? And you see that in order to get to the really high neutron-rich, really high yields of neutron-rich species, you need progenitor metallicities that are just unreasonably high. 5, 10 times solar for the progenitor of a white dwarf. And these are stars that are not common in the Milky Way. If you can find a way to measure these yields, you can hope to distinguish between these two possibilities, a Chandrasekhar mass progenitor and a sub-Chandrasekhar mass progenitor. The problem with doing this in the optical is manganese and nickel are notoriously hard to observe. You can do it in nebular spectra, but you need to take the ionization effects into account. Manganese you can't even do in the optical because the progenitor of manganese, which is cobalt-55, has a half-life of 3 years, so you never get enough manganese to see it in optical spectrum. But you can do it with supernova remnants, again using the high effective area of Suzaku at these energies. And this is something that I and other people have worked on. You look at the high energy band between 5 and 9 keV, and you can see that besides your good old friend the iron K alpha line, you have these other lines here that are lines from chromium, manganese, and stable nickel. Now, this is interesting, and I have used this to put constraints on the progenitor metallicities of Tycho and Kepler, together with my collaborators. But these young objects are not where you want to look, because these are young objects, and they have not, the reverse shock in these objects has not reached the interesting part, where these neutronized species are, right? The neutron-rich NSE regime. You need an object that's very evolved, something that's a lot older than Tycho or Kepler. So this is when we go back to this plot, and this is why it's wonderful to have this plot, right? So we want something that has a lot of iron and is evolved. So meet my new friend, Supernova Remnant 3C397. I forget these phone numbers too. Don't feel bad about it. It's like a supernova remnant, right? It doesn't have a memorable astronomer attached to it, so it's easy to forget. But in this case, the reverse shock has reached the neutron-rich nuclear statistic equilibrium regime, because this is an object with a very large dynamical age. So this is where you want to look, right? And I'm not going to give you the details about this. I'm just going to show you the X-ray spectrum of this guy. Now, I've been looking at X-ray spectra of supernova remnants for 15 years. That's a long time. Not as long as some people in this room, but long. I've never seen anything like this. That is a whooping line from stable nickel. Very, very, very bright. About 1/10 as bright as iron K alpha. So without doing any analysis, this is way supersolar, nickel to iron. Okay? But of course, you want to take this spectrum and put it in the plot that I just showed you, right? So how do you do this? Well, this is where it's great to have people like Randall who work on the atomic data for these things, because if you want to turn this line flux measurements into mass ratios, you need the atomic data. And I want to really take, even if it's just 1 minute, because I'm running out of time, I want to take 1 minute to make it clear to everyone that the atomic data are an integral part of this. I know atomic data are boring, but they're crucial. Okay, and of course, the atomic data for iron are in pretty good shape, but nobody really worried about chromium and manganese and nickel before, because we really didn't have any detections, right? So what are you going to apply this to? But anyway, you can do it. And if you do it, you get this very, very interesting result. Now, again, this is the same plot that I showed you. The blue points are the delayed detonation Chandrasekhar mass models. The red points are the sub-Chandrasekhar models. Again, you can get to the high neutron-rich species yield regime if you just crank the metallicity unreasonably high, but stars like that really don't exist plentifully in our galaxy. Right? Just to give you an idea, this is where Tycho and Kepler are. Again, these are measurements that are not very interesting because they have no diagnostic power. You haven't reached the neutron-rich NSE regime. But this is where our friend 3C397 is. It is in a part of the diagram where if you want to make this work with a sub-Chandrasekhar progenitor, you would need 5 or 10 times the solar metallicity. And to find one of the most metal-rich stars in the galaxy by chance when you look at the first evolved supernova remnant that you get your hands on is just very, very unlikely. So what we're seeing here is, in my opinion, and I'm giving the talk, so that's the opinion that you're hearing now. So I think this is probably the most robust measurement of the mass of a Type 1a supernova progenitor today, because really you do need the Chandrasekhar mass progenitors. More details in the paper. This appeared this week in AstroPH. And just to reassure you that you really need the electron captures here, what I'm showing here now, the red points are the part of the Chandrasekhar mass progenitors that is not in neutron-rich NSE. Right? So I'm just separating the red points. This is a little confusing. They're not the sub-Chandrasekhar models anymore. But this is where the neutron-rich NSE part of the models is, and this is where 3C397 is. This object is really dominated by neutron-rich nuclear statistic material. And the only way we know how to get that is if you have a white dwarf whose mass is very close to the Chandrasekhar limit. Okay? So where are we? From my point of view, in a very uncomfortable situation. Because, I don't know if you remember this, it was like a few slides ago, but I am on the record in the refereed literature, for whatever that's worth, saying that most Type 1a supernovae, or maybe all, could be double degenerates. And this is pretty much the end of it for me. I don't know of any other way to explain this particular object if it's not with a single degenerate progenitor. I mean, all the other indirect evidence hasn't gone away. We still have looked for the companions and haven't found them. We still have the delay time distribution, and we still have this high white dwarf merger rate. So the logical solution is that there may be a mixture. Type 1a star-forming galaxies probably come from a mixture of single degenerate and double degenerate progenitors. And again, I have to reassure you, I really don't like this. If you find a way to get rid of this, I'll be happy, but you know, things are what they are. Just to recap, we've looked at the iron K alpha line in Type 1a supernova remnants, and we've seen it's a wonderful diagnostic, both of supernova type and quantitative tests for the progenitor evolution scenarios, because it really puts very interesting limits on the amount of ambient medium or circumstellar medium interaction that you can have. And this is interesting for both 1As and core collapses. And I expect there's going to be quite a deal of follow-up work on this paper. Dynamically, most Type 1a supernova remnants are compatible with little or no circumstellar medium. So, and this has to apply to whichever fraction of those are single degenerate progenitors too. So, you know, there has to be a way to make a single degenerate progenitor without dumping a lot of material in the ambient medium. Chandrasekhar mass uniform ambient medium models work really well. That doesn't mean that other models that we haven't tried are not going to work equally well, but the simplest thing that we have tried really worked well. Again, I want to mention at least RCW86 is different. That is one of 12 supernova remnants, so I don't know what that means for things like populations of supernovae that explode in faraway galaxies, but that particular object does not conform to this picture, okay? And again, the logical explanation for that is a single degenerate progenitor, because you need a fast outflow from the progenitor that is sustained for some time before the explosion, but I don't consider these as clean as what I just presented in 3C397. This is, I think, a very clean, very robust measurement. It doesn't really matter what the details of the supernova nucleosynthesis calculations you do are. If you have enough density in the core of the white dwarf, you are going to get neutron-rich species. That's unavoidable. And there really is a lot of neutron-rich material in 3C397, so that's essentially what it is. But again, as I said, the other measurements that show a preference for the double degenerate scenario have not gone away. So maybe part of the reason it's been so hard to make progress in this problem is that we're looking for smoking guns and falsification schemes for scenarios that are really coexisting. I see we're hitting the 50-minute mark, so I'm just going to stop talking and take questions if you have any. Thank you very much.
Thanks very much. Please, questions?
Randall.
In some sense, is there any way to avoid, imagine that you've got a fairly close-in binary system that is accreting. Isn't it someday going to, how could you avoid ever getting a single degenerate if you had that kind of system? It couldn't live forever. Eventually, the two things are going to spiral into each other.
You mean the single degenerate accreting in the usual way through Rorschach overflow?
Right.
So the answer to that question, unfortunately, passes through our understanding of accretion and nuclear burning on compact objects, which is sketchy. Yeah, and especially degenerate objects, because this is, you know this, the equation of state is decoupled from temperature. You're just putting energy, and this is a situation that's rife for instabilities. And that's what a nova explosion is, right? It's a thermonuclear runaway on the surface of the white dwarf. So a lot of people have tried to argue, well, I'm going to make novae, and then bam, type 1a supernova. But whenever people have looked at this in more detail, at least the nova that we observe, they seem to erode the white dwarf, remove more mass than they put in. And that's a problem. And people have been working on this for a long time, and again, without necessarily making a lot of progress. So sometimes you catch a certain wave of desperation in the community. I've heard people trying to argue that you could make a subtransector white dwarf explode in that kind of scenario, too, right? Then why does it explode, right? When does it decide that it's had enough? I don't know. Again, the theoretical literature on this is truly hard to keep up with because, some people call the merger models collisions because they're or violent mergers, and Noam Soker has something called the core degenerate scenario that he's very fond of telling people about. There are many variations of this, but you have something that's accreting. It doesn't necessarily mean that it will get to the Chern-Senker limit. It's complicated. Yes?
I agree with your conclusion, and I like it very much. My interest in this subject is I've been through studying the potential progenitors and the accretion in interacting binary systems, including symbiotics. Another sketchy part, I believe, is the accretion. How is the accretion done? It's not Roche law, maybe in most of the cases. It's a focused wing accretion.
Using gravitational focusing on the...
That's right. And that's the part that we are doing observation. And I've seen these two groups, that either you're here, either you're here.
That's becoming more and more untenable.
Yeah. In between, with a fraction of them being single digit.
My question to you then is, my understanding is that the accretion rates you can get through gravitational focusing of the material on the white dwarf are pretty low. And you do need the white dwarf to grow by a substantial fraction of a Chern-Senker mass in this time. And you can't afford to wait forever because we know type 1a supernovae explode a few 100 million years after star formation. So,
the quoted rates are Bondi Hoyle. It's 1% or something smaller. The models that we've done, the both Boro, myself, and so on, and Potciel-Dobson, which whom you quoted, it shows that can be order of magnitudes and higher, actually, through this focus.
And that's enough to get explosions within a few hundred million years?
That's the question, but they're much higher than what they're used in the regular models.
Okay.
Yeah, I think this question of whether there are two populations is something where the homogeneity of the spectra argues against it, but the differences in the luminosities might support this. That is, we know, for example, that the supernovae on average in the elliptical galaxies are different in luminosity from the ones in the spirals, and so you might think that if there's a fast population and a slow population and they come out slightly different luminosities, they would presumably correspond to these two paths of evolution. The problem has been knitting all that together in a
consistent
way, but it looks
picture
to me like the evidence that for two populations is pretty good.
It is, and I have to admit, maybe because I have somewhat of a more naive tendency to look at simple models that can explain everything. I have to admit I've been drag kicking and screaming into this, but I can't find a way out. So
I never liked those double
so there you go. I think John had a question.
Yeah, if you look at a couple of the type 1 remnants like Kepler and N103b, it's clear that what they're running into is not uniform. There's
Yes.
radiative, non-radiative shocks, density contrast of a factor of 100. So the question then is when you do when you assume an ambient medium, an average ambient medium, are you really just sampling sort of the interclump part of that?
Yes. That is an excellent question, as I usually get from John. But again, and let me go back to this plot. Yes. Uniform medium is exceedingly naive, especially in those scales, right? We know the interstellar medium has a lot of structure and it probably looks fractal, especially in scales of a parsec or so. But whatever is going on, it does not drive the 1As to be here. So there is a point in which you're just dumping enough mass in the circumstellar material that dynamically the object starts to look different. And again, as I said when I was showing this cartoon the second time around, you could think of cavities close to the objects, and then maybe something a little milder going on. We're not ruling out any of these scenarios, but whatever the final answer is, deviations from this can be truly large. Because if they were, these guys would be over here with the core collapse remnants, and they're not. So, of course, somewhere in between very little and several solar masses of circumstellar material, it lies our answer, right? And we need to do more modeling.
I think it's a question of what the averaging is when the shock wave runs into this stuff. So if it's condensed into very, very dense clumps, then the iron isn't even going to see that really. But the question is how dense, how clumpy it would have to be in order to give a big underestimate of that.
Yes, and it is as I said, it's a very good question. And I mean, one thing we know about every accreting white dwarf system we've looked at, they have very homogeneous environments. I mean, you look at Ares of Fuki, it is anything but uniform. But again, Ares of Fuki is a very good example. If Ares of Fuki exploded tomorrow as a Type 1a supernova, and you waited for a long enough time, my guess is that it would be more close to this, because there's a lot of mass there, right? So there are people doing this kind of models actively. I think Patenaude has a student working on this, a postdoc in Oxford. So we'll find out more. Oh, Jared.
I would like to suggest a way out.
Please do.
If you can go back to your DTD plot.
The delay time distribution?
Yeah.
Type 1a delay time distribution, that was back here.
Yeah. So this is not a criticism. The dots need to be clear in that we have anywhere between 3 and 8 1A prototypes, just like Obia Fine Grill Kiss Me. And we don't know, we have debates, but we don't know why any of those exist and how they connect to maximum light spectra, day minus 14 maximum light spectra, and a year after, or the remnants. So
you're saying that this, we may be trying to measure the delay time distribution of something as a mixture of many.
A mixture, that's all. It's not one or the other, it's just a mixture. And so
completely agree. I mean, when you play this game, you're making the underlying assumption that all Type 1a that explode everywhere in the universe are more or less equal.
That's all. And
And we know at some level that's not true.
Yeah, I don't think it's the only solution. I just think it's part of the path there.
Point taken.
Very good, very good. Well, with that, we'll thank Carlos again. Carlos is around, he's around tomorrow, but he has a very packed schedule, so maybe you'll catch him in the hallway, or maybe you want to email him directly, see if you can find some time. Again, thank you very much.
Thank you.